Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's make a start. So this is our last hour together for a little while because you guys have a break coming up, so better make the most of it. All right, so last time finished up talking about coplots. So this is an example of a coplot. Like I said yesterday, the co in coplot stands for conditioning. And so the idea is that we're looking now to take this sort of six-dimensional data, summarise some number of those dimensions, but in a two-dimensional space. Because, you know, we're stuck with a screen that's two-dimensional. You know, the best we've been able to do up until coplots was age versus weight, taking up the main two dimensions, and then coding for survival. So we get that third dimension by using empty and filled symbols. And now we can bring in the fourth dimension by taking another variable, in this case 1 minute APGARs, splitting it up into low and high, and showing a plot for age versus weight, coded for survival when APGARs is low, and then the same thing when APGARs is high. And the idea is that as you move from one plot to the other, you see the impact of APGARs on the relationship between age, weight and survival. Okay? As I mentioned yesterday, how coarsely you divide APGARs is up to you. You could say to yourself, right, I'm going to produce a separate plot for APGARs 0, APGARs 1, APGARs right up through 9. Two problems. The first one is that the number of data points in each plot is going to be significantly reduced, right? Because there aren't that many babies for whom APGARs was 0. And so you'd have a plot with maybe 2 or 3 points on it. You're not going to see anything there. If you've got 3 points in a plot, you see a triangle, no matter what you try to do. Okay? So you're going to have that problem of low data density. And then the other problem you have is that you're trying to perceive gradual change as the APGARs slowly steps up from 0 to 1 to 2 and so on. And gradual change is hard to perceive. And then you've got to ask yourself, well, is it worth perceiving it if those changes might be basically over-interpreting noise? Okay? As you move from APGARs 0 to APGARs 1, you've probably got a baby that in both cases is fairly hard to see them surviving, and so maybe the relationship's not going to change much at all. Okay? And you're being asked, there'll be noise, obviously, and so then there's a question of, well, am I over-interpreting noise? Which is a big problem, of course, in statistics. So, yes? How to interpret noise? Yep, that's a really good question. The answer is you don't know, right? We know the data's noisy because when you look at any of the scatter plots, you might think that the relationship within each one is linear or strong, but even with a strong relationship, you've got points that are away from what you imagine the relationship to be, and that's noise, okay? So all relationships in statistics seem to have this problem where you've got signal and noise competing, okay? And so the whole idea of fitting models is to say, well, I think this signal is very much stronger than the noise. And a t-test is basically a signal-to-noise ratio. It's basically saying what's the signal, what's the noise, take one, divide by the other, If that number's big, then I think my signal's real. Okay?
If I not use the test time, just find the plot, add a Lewis curve to see that.
Yeah, absolutely. So a lot of the time your eyes will tell you whether a signal is real or whether it's not. But sometimes the test that you do in your head is not quite the right one. Let's suppose we're talking only about straight lines, okay? When you look at a plot and you see a straight line model, the t-test compares that straight line with white noise, that is no structure at all. And maybe that's not the right comparison, right? Maybe you should be comparing that line with a different relationship that might be curved and stuff like that. And you don't get those kinds of comparisons very easily, either visually or through testing. And it's a real problem in statistics. There is some thinking at the moment that the failure of statistics to allow studies to be replicated in medicine and in psychology is largely due to the fact that humans produce data that's incredibly noisy. So, I mean, there's some very challenging problems at the moment. So if you go back through, psychology has been infected with it. So if you go back over the last 100 years in psychology, there are tons and tons of studies, right? Things that, most people now accept as true about the way human minds work. And so recently, a group of scientists decided we're going to take the 100 most popular psych studies and we're going to try to replicate them. So they took the 100 big-ticket psych experiments and they said, let's do them over and see what we get. And they could only replicate fewer than about 30% of them. The other 70% didn't replicate. The effect that we all believe is real actually disappeared in the experiment, wasn't present. This set psychology, they went nuts, right? If you Google, I know Google's been in the news this morning because Trump mentioned that, Google has nothing nice to say about him, okay? Anyway, if you Google reproducibility in psychology, you'll see there's literally hundreds of papers now about how psychology has failed to replicate key experiments. Even more frightening, recently I read that about half of all studies into cancer are not replicable. And that is scary, right? And it's scary because, let's face it, if you have cancer, you are so relying on treatments working. And a lot of the science that we thought was solid as rock is not. I mean, you might be getting treatments that make you a lot sicker in some ways, and they're just not going to work because there's no ability to replicate. This is all due to noise, right? So noisy data is a real problem in statistics. And we rely on testing and we rely on visualisation. And, the truth is that we really need also to be designing experiments that sort of design out the noise as much as we're able to. But we ultimately have to accept that noise is a part of the deal. So you've asked a very, very good question. It's probably the fundamental question that's getting asked in statistics at the moment, is where are we going? Is statistics actually not helping us? And it's all because of noise. So we do our best is the answer. And visualisation is one part of the evidence base that we can build. One of the messages of this course is that you have to go beyond just testing. Because when you just test, you're testing some reality against models are wrong, but they might be good enough. The problem is they're not going to be good enough for every purpose. And so supplementing that evidence with visualisation is actually increasingly important. So it's a really good question. Okay, now I need to show you how to do this plot in R. It's a little bit complicated, so we'll take our time. Okay, so this is the code that does it. It's in the blue here. I'm going to leave it in the blue so you can easily spot it when you look up. So, okay, the first thing I need to do is I need to divide the data into the two parts when APGARS is low and APGARS is high. So I'm going to create a new indicator variable, which is going to be baby 4 less than or equal to 4. Okay, so APGARS are going to be low when they're 4 or lower, and they're going to be high when they're 5 to 9. Okay, so that's going to give a true when they're low and a false when they're high. Now, next thing I do, I'm going to set this out as two plots. I'm going to put them one next to the other. Okay, We worried previously about whether you should put things side by side or one on top of the other. It doesn't really matter in this case because there's no sort of common axis that you want to cleave to. If you put them one above the other, I would recommend making the x-axis the same for each plot. If you put them side by side, I'd recommend making the y-axis the same, okay, because that's going to draw the comparison. One thing that's always worth doing when you're constructing a graph is to do it both ways and see which one tells the more effective story visually, okay? So if you're going to do them vertically, what you do, make your window narrower than it is tall, okay, so it's nice and tall, and then you go MF row equals C21, not 1, 2. All right? But for the moment, we'll stick with 1, 2. The OMA equals C4060. Remember, sides of a plot are numbered from the bottom, so this is the bottom. So that gets 4, we're leaving 4 lines of space. The reason is so we can put in subtitles, okay? No space at left. 6 lines at the top to put this nice big title at the top, and no lines at the right. A lot of times people ignore that bit, they don't set their margins right, and then what happens is when you try to put your title on the top, it doesn't fit and you get an error message. So if that's ever what happens to you, you need to set that out of margin. All right, so now we need to set up both plots. We do it one at a time. So the first one, we plot age versus weight, type equals n. So again, we use a blank plot to start with. Okay. Here's my survival variable, which is 1 or 0, depending on whether the baby survives or not. And now I need to put points on. So I'm going to put the points on in 2 waves. First of all, I'm going to put the points on for the babies who have low 1-minute APGARs who do not survive. Then I'm going to come through and put in the babies that have low 1-minute APGARs and who do survive. This is only for the low APGARs. So how do I subset that? Okay, this is the part you need to look at. So let me construct this line by line now, just so we can see it grow. So there's the first empty plot. There's my survival variable. Now I'm going to add the babies that did not survive. All right, how do I do it? I use the fact that when you have logical variables, true-false variables, multiplication does a very nice thing. It's like AND, okay? So if true and true is true, anything and false is false, okay? So true times true is true, false times false is false, false times true is false because one of them is false, and vice versa. True times false is false also, okay? So if I take IND and I multiply it by not survive, I get only those babies who have true for low 1-minute APGARs and true for not surviving. So these are the 1-minute APGAR babies who are low APGARs and didn't survive, okay? So that's why I'm doing that. And I have to render it as a true-false, so I go as.logical. If I leave it just as a multiplication, it converts it to numbers, all right, which you don't want it to do. So a little bit of a complicated thing here, something that's a bit new to us. So we take 2 logical variables, my indicator for low 1-minute APGARs and my indicator for survival. I multiply low 1-minute APGARs times not surviving. I turn it back into a true and false by using as.logical, and then I feed that into the points, and I get only those babies with low 1-minute APGARs who did not survive. All right, next step. Let's put in the babies with low 1-minute APGARs who do survive. And again, very similar, except now when I take that indicator for low 1-minute APGARs, I multiply it by survival, not survival, okay, instead of not survival. Okay, and that puts in those points, and that's my first plot. You'll notice I've got a lot of space at the top, got a little bit of space at the bottom, no space on left and right. Okay, now I put in the second one. Here we go. There it is. Add in the babies. This time it's the babies with high 1-minute APGARs, so it's not IND multiplied by not survive, turn it into a logical, okay? And then I put in the babies with the high 1-minute APGARs who do survive, Okay, so you've got to build this thing. It's like layers. And once you build all those layers in, you get the plot that we see here. The very last thing I do is I put a title on the whole lot. So M text stands for margin text, so I'm putting text in the margin. I put the text that I want to use, plot of survival against weight and age. The 3 is the side I'm putting the title on, so I want to put it on side 3. Remember, I number from the bottom. Bottom's 1, left is 2, top is 3. So I'm putting it on the top. If I wanted to put it on the bottom, I'd use a 1, not a 3, okay? Outer equals true. CEX equals 1.5. I want to make it a little bit bigger, okay? So, that's the plot I end up with. So, I mean, it'd be lovely if you could just go, bleh, do a plot in one line. It don't work that way. You've got to build it. That's all it's doing. If you want to put a subtitle, you would use mtext again, but you'd use side equals 1, not 3. And you could probably put CEX equal to something smaller so it's a little bit understated. You don't want your subtitles to be shouting, right? That's a good question. I'm looking at it thinking to myself, what's that 1 doing there? Let's find out. Always, this is the great thing about R is if you want help, you just say help. Side equals 3, line equals 0, so it's line. On which margin line? Starting at 0, counting outwards. Okay, so we've left 6 lines of text available at the top. Okay, we're counting outwards, so 0, 1, so it just puts it a little bit above the pictures, not too far above. So you can see because we didn't use the subtitle, the effect of putting those 4 lines in the margin just makes the plot a little bit shorter. So that makes it look a little bit better. I can't remember when I did this, but my best guess is that when I first produced it, I wanted it to be just a little bit away from the edges of the page, so I manufactured that. That's why I've got 4 lines at the bottom. Okay, so if you use line equals 1 with 6 lines of text, it'll put it on that second one up, which will leave 4 lines at the top, which will centre it. So you can mess around with that. For instance, if I re-put that on, but I put line, instead of 1 here, I put 4, it should put another title above that one. Let's see what it does. There it goes. Yeah. So that's how you mess with that within the margin. Okay, so that's coplots. Now, like I said to you, wouldn't it be wonderful if R could do coplots automatically so I didn't have to do all this myself? Well, I got good news and I got bad news. What do you want first? The good news or the bad news? You want the bad news first. Some people are just pessimists. That's not good. The bad news is you've just dropped your phone. No, the bad news is even though R has a coplot function, it sucks. It doesn't really do what you want it to do. That's the bad news. The good news is that R has a coplot function. Okay? That's the good news. No violence in the class. All right. So let's talk about coplots. To do that, I'm going to look at a different data set because I want to show you R's coplot function and talk about why it's not a great choice. Okay, so this is some new data. Cement data. Let's go back to the notes. So we're done talking about the babies for the moment. I'm going to come back. Sorry, I need to be in chapter 4. Okay, let's talk about cement. It's a very famous data set. Very relevant in the ACT, and I'll tell you why. So when people lay cement, very often over the top of the cement they put like sackcloth or hessian cloth, so breathable cloth. And the reason that they do that is because when cement dries, it dries by giving off heat, and if it gives off the heat too quickly, it cracks, right? So you might remember me telling you about running around in the ACT on footpaths and how dangerous that is? Because, I don't know if you've noticed, but every footpath you walk on in the ACT is cracked. Have you noticed that? Well, pay attention, because you can trip over. It's not good. Certainly if you run out in the suburbs and you're running on footpaths, you're all the time worrying about where your foot's going, because all of the footpaths are cracked. The reason they're cracked is because of the temperature differences you experience in Canberra. It gets very cold at night, and then it warms up to reasonably warm during the day, even in winter. I know you might not think that. In summer it gets hellishly hot. And so you get these large, what they call diurnal temperature ranges, because we're inland. And what that means is when they lay footpath, it's cracking all the time, right? Even with newly laid stuff. So you might think, well, okay, that's cool, interesting story. Why do I care about that? Well, scientists care about this sort of stuff. What they'd like to do is to be able to make cement that doesn't do that. And so there's a data set, very old data set, which has, and the reason I'm using an old data set is because it's very small. You've got 13 observations from an experiment that related the heat that comes off the cement to the percentage of 4 chemical constituents of that cement. And they have some delightful names. They are tricalcium aluminate, tricalcium silicate, dicalcium silicate, and calcium, it's aluminum, it should be, aluminium ferrate. Okay? So these variables have the name Ca3a, Ca3s, Ca2s, and CaAF. Okay? Now, if you change the amount of each of those chemicals that goes into cement, when it dries, different amounts of heat come off. Okay? So you can mess with how you compose your cement and you'll change the heat composition. So the idea of this experiment was to say, how can we get cement that doesn't crack so much? Right? So it's a nice change, right, from the data sets we've looked at. So we started off with the star data, which is about the universe. It's very, very broad. Then we talked about rats, which is a bit sad for the rats. Now we're talking about cement. We talk about anything. Statistics is wonderful because it lets you talk about anything on God's green earth. Okay? This isn't even green earth. This is cement. So there you go. Old data set, the reason we're talking about it's got 13 data points, only 13. You might go, why didn't they collect more data? Well, back in 1960, if you wanted to fit a model and you had, 20 data points, you're in a world of pain. You didn't even have a calculator, right? You didn't even have a calculator back in 1960. They didn't exist, okay? By the way, you might say, what did exist? Let me show you. This is cool. You look up calculate, well, you're supposed to spell it right, calculating machines in Google. You go to Google Images, you see these pictures. Now, this is a true story. When I was an undergraduate, which is in the 1980s, early 1980s, the room we did statistics in was a regular classroom. We didn't have any computers. PCs were not a thing, okay? They just weren't a thing. There were computers at the university. This is University of Queensland. There was a computer called the PDP-11, okay? It sat in a building. I think the room that the PDP-11 was in was probably about the size of this room, okay? And it was filled with the computer, right? That computer was about 1,000 times less powerful than that. Seriously, right? So I carry in my pocket these days, well, the thing you carry in your pocket these days is about 1,000 times more powerful than the computer that got man to the moon. Seriously, that's how life has changed. So when I did statistics, if you wanted to do computations and fit models, you had two choices. You could use the PDP-11, but you had to book time, right? You had to book time to use it. And there were no keyboards. So you had to get punch cards. You had to punch your programs onto punch cards. And so a program might have been a stack of cards about this high. Seriously. And you'd put it in the little card feeder, right? And it would pull them through on a tractor feed. There wasn't anything automated about it. It was pretty slow. Every time you had a syntax error, everything would stop. You'd have to find the card the error was on, repunch it, put it back in and do the whole thing again. And you wonder why we got grey hair. Right? It's horrible, right? That was the way life was. There was another way. You had a calculator, okay? And so when I was your age, if I wanted to fit a model, I couldn't ask R. R was about 20 years from being developed, right? So you had to do sums of squares calculations on your calculator, all right? So imagine what life would have been like. Well, I don't have to imagine, I lived it, right? Anyway, in the room where I had statistics lectures and tutorials, at the back of the room there were rows and rows of these. In fact, I think I can show you the exact one they had. I think it was that one. Okay? And these things, amazing machines, right? Because there's nothing digital about it, right? You don't have to plug it in. See this thing here at the side? You cranked it. You turned the handle, right? This thing didn't have electric power going into it. You literally cranked the handle and it would roll digits and calculate sums of squares based on what data you punched in. Isn't that incredible? So, why am I telling you the story? Back in 1960, this was about it. It's about all you could do. If you had more than 13 data points, you were screwed, right? You know, you come to today, and today you have data sets that have millions of data points and no one thinks about it, and it's all R's responsible for it, it's all cool, and we cope somehow. By the way, and again, this is a bit of an aside, but hey, it's our last day before we have a 2-week break, so let's talk fun. There are now data, I mean, it doesn't matter what the technology is, the need is always one step ahead of it, right? So currently, there are data sets that don't fit in the memory of any single computer. And so there's this distributed computing movement where what happens is you have this big data set, it doesn't fit in any single computer, so you have to split it up into smaller ones. They get farmed out to different computers. These are big computers. And then the answers come back and they have to be recombined. There's a whole set of new computing going on that allows you to deal with literally data sets that are, you know, thousands of times bigger than, say, your PC can handle. So, you know, we look back into 1960 and we say 13 data points, how primitive. In 10 years' time, you'll be experiencing what I experienced, which is what you did at uni will look weird and weak compared to what is currently being done, right? So life has a way of moving forward, whether you go with it or not. And it's a really interesting way to think about things. So we had these. So I've used one of these to do sums of squares calculations, right? You'd think I would have developed muscular fingers, but it didn't really happen. But yeah, cranking the handle was the worst part, right? You'd go home and your arm would be sore. And Mum would say, what were you doing all day? Why is your arm sore? And you'd tell her this and she'd think you were lying because who would do this and all that. So anyway, pretty cool stuff. So that's why 13 data points doesn't seem so weird back in 1960. The other thing I'll say about this is that the 13 data points, and why you might say, well, okay, that's all very cool. We love hearing your stories. I'm just making up that you're thinking that, because I know you're probably not. But we love hearing your stories, but, you know, get real. We're not in 1960. Why do we have to relive this nightmare? Why are you still talking about data sets with 13 data points? Well, here's the challenge. This is 5-dimensional data. You've got a y and you've got 4 x's, and you've got 13 data points, right? Welcome to the world where n, the number of data points you have, is not very big compared to p, the number of covariates you have. And again, this is a problem that's currently occurring. In life these days, we now have small data sets, right, where small might be in the thousands, but huge numbers of covariates, right? What do you do? And so the problem of dimension reduction becomes even more stark when you've got very little data on which to base your decision making. So this is kind of a small example of a data set where the dimension of the data is way too big for the amount of data you've actually got. And what hope do you really have? And so visualisation is really a very powerful way forward. So let's read the data in, and then I'll show you the data. So here's the data. So y whoops. Let me type this here. So x is this, and y is this. So there's my two sets of variables. So my response variable, which is the heat, are these, and these are my 4 x's. Okay, there's 13 of them, as I said. All right, what's the first thing to do? Well, whenever you look at any reasonably high-dimensional data, a scatter plot matrix is where you start. And so let's have a look at that. And what I'm going to do in this case, as we talked about before, I'm going to add lines to each of these panels, just to make it a little bit easier to talk about. So even though it's only 13 data points, you can see structure here. I mean, it's not tight structure, but it's structure. Again, we're looking in the top part, the top triangle of this, this set of graphs. The reason we're doing the top one is because y is at the top, and so all those 4 graphs along that top row have y as their vertical ordinate. Okay? So that first plot in the top row is y versus CA3A, or y versus x1. The next one is y versus x2, y versus x3, y versus x4. Okay? So we can make some very quick judgments about what's going on here. If you increase x1, then y increases as well. Okay? If you increase x2, y increases as well. If you increase x3, y decreases. And if you increase x4, y also decreases. Yep. Y is the amount of heat that comes off in calories per gram. Yep. Okay. Now, you've all got good eyes, so let's talk about this. What do you think? Are there strong relationships? Are there weak relationships? Are they significant? What do you think? What about y versus x1? Is it strong or weak? Pretty strong? Yep. That line's not flat. Doesn't look like white noise. So, yep. Y versus x2, strong or weak? Very strong, so stronger than the previous one, I agree. x3, strong, very strong again. And x4, probably the weakest of the lot, but it's still not negligible, still not flat. Okay? So it looks like, on the face of it, that y is related to each of the x's. Okay? Now, just before we start trying to draw pictures, let me fit a model, because models sometimes tell you lots and sometimes they make you feel a little bit unhappy. So I'm going to attach x. What that's going to do, this is an interesting point. So x is this matrix, it's got 4 columns with names. I wanted to attach it so I could use the names. When I tried to attach it, it said, you can't attach this, it's not a list, a data frame or an environment. How do I fix that? I go attach as.data.frame of x. This is a good trick. If x is a matrix, it won't let you attach it. Okay? It has to be a data frame to attach. So all I do is I take x, I interpret it as a data frame by using as.data.frame, then I can attach it. Once I've attached it, I can use the names of the variables. Okay, so here's my model. Model equals RLM of y tilde, and here I give it the variable names. It's CA3A plus CA3S plus CA2S plus CAAF. So I've gone ahead and fit the models. The model, I should say, only one of them. Now, let's have a quick look at what this model says. So this model says y equals 56. So that's the value of heat when all of the x's are 0. So let's think about that for a second. If all of the x's are 0, what does that mean? Well, you don't have cement because you haven't put anything in it, right? These are the chemical constituents of cement. So if they're all equal to 0, it's not cement, it's air, right? So this number doesn't have a physical meaning. And in a lot of cases with models, the intercept doesn't have a physical meaning, just where the line would go if it could go down that far. So we're not going to worry about the intercept so much because it doesn't really make any sense, but it anchors the rest of our model. Okay, so you've got an intercept, pardon me, plus 1.61 times that variable, plus 0.56 times that variable, minus 0.08 times the third variable, plus 0.18 times the fourth variable. Now, have a look at those numbers. Something should now be bothering you. What's bothering you?
It seems that CH2S and CH3S have a relationship, so
Yeah?
a problem on multiple linearity exists.
But there's nothing about the model should bother you in that sense, right? Because when CA3S goes up, the number's positive, so the relationship goes up. When this goes up, it goes down, so that's negative, so that's cool. And you've spotted it. Yeah, absolutely, right? So the coefficient of the last one, you look at that slope's negative, then you look at this, and it's positive. So if you make this thing go up, y is going to go up, right? Because that's positive, and that's not what happens. So what's wrong? How did this happen? This happened because collinearity, exactly, right? So remember that linear models work on the basis that the coefficients are the amount by which y would rise when each individual x rises if all the others are held constant. Problem is you can't do that and make cement. If you put more of one thing in, you have to put less of another thing in, or vice versa, so that the thing holds together, right? These things interact with each other. So interpreting models is really hard because of this feature, okay? I'm going to go ahead and refit the model just using LM, not RLM, because I want to show you something. Actually, no, RLM's fine. I'll keep going. I'm going to use a summary of Model 1. Not Model 1. There's my summary of Model 1. Okay. I am going to go back and use RLM because RLM does something nice. Sorry, LM. LM does something nice for me. So, summary of model. So here's my summary. Okay. The reason I used LM instead of RLM is that LM gives you p-values. With RLM, I'd have to calculate them. Not hard to do, but just to cut to the chase a little bit. So there's my fitted model. There's the coefficients. You'll notice they're a little bit different than the other ones because LM and RLM use slightly different fitting mechanisms. Same problem occurs though. Positive, that's fine. Positive, that's fine. Negative, that's fine. Positive, that's not fine. Okay, based on the picture. So same thing happens. Here's my p-values. Now remember how p-values work. And again, this is not an endorsement of p-values, let's be clear. But if we went the p-value way of life, remember if p-values are smaller than 0.05, then the coefficient is significant. Okay? None of these are bigger than 0.05. Right? So not significant, not significant, not significant, almost significant, but not, and not significant. Right? None of them are significant. Right? What does that mean? Does that mean none of them work? Then you look at this picture and you go, well, of course they've got to work. Look, there's a relationship there. I see the relationship. How can it not work? And then you look at the p-values and none of them work, okay? Welcome to the world of multivariate modelling. This is what happens. And it happens because these guys, they're all related to one another. So you can't pick them off one by one and go, this one's not important, and then this one's not important, and then this one's not important. You can't pull it apart that way. And this is, for people who study regression, the first disturbing thing that happens, right? Things that are simple aren't simple anymore. In linear regression, things are simple, right? You change x, y changes, and in a predictable way. You look at the sign of the coefficient. If it's positive, it goes up. If it's negative, it goes down. Done. Multiple regression? No. You raise this guy, y goes down. Uh-oh. So you've got problems there. And this is why visualisation is so important, right? This is why visualisation is so important. All right, now, let's have a look at a few of the different plots that we've had before to try to make a bit of headway in understanding this particular data. So I'm just going to start by... let me make it... So this is a symbol plot. The symbol plot, remember, is an attempt to try to get some high-dimensional data into 2 dimensions. So I've been a bit ambitious here. I've got... Oh, by the way, last time when we had a binary response, we had the benefit of not having to plot the response on the y-axis. So we plotted weight versus age, which were 2 of the covariates, and then we coded empty versus filled for the response. Okay? Can't do that here. We have a response variable, which is heat. Okay? So that's got to go on the y-axis. That's one axis now taken. Okay? So on the other axis, we put one of the variables. All right? So we've chosen to plot y on the vertical axis and CA3A on the horizontal axis. Now, what we've done in addition is we've created symbols, and we need to encode the other 3 variables. Okay? So to encode 3 continuous variables, you need to use stars. So stars has 3 elements, and they are basically the little rays in a star. So what does a star look like? I'll draw it nice and big over here. I'll also describe it for them who's watching at home. So, okay, so this might, you've got a central point, and you've got rays or lines emanating from the central point, and the lengths of those rays are equal to or proportional to the values that you're trying to encode. So if I've plotted y versus x1, then the star has rays whose lengths are proportional to x2, x3 and x4. Okay? And then what R draws is not the rays themselves, but it draws the skeleton, sorry, it draws the shell, or the, I can only use a mathematical term because it's all I can think of, convex hull of the skeleton. It puts skin on the skeleton, basically. Okay? So this inner bit you can think of as a skeleton, then you skin it by putting skin on it, not taking skin off it, and that's what you're looking at. So on the screen you see little triangles, and you kind of got to imagine, because R doesn't draw them, these bits here. Okay? Now, when you think about that, you can sort of see that the shape of these triangles tells you something, right? If it kind of looks like it's pointing sort of up and to the left, as say this one is, this tells you that, let's see, I've got to get them right, but it tells you that x2 is small, x3 is big and x4 is small, okay? So the direction of the triangle kind of tells you the relative sizes of the bits. And so you can see when you look at this picture, something happens as you move from bottom left to top right of the graph. You can see that the triangles go from being roughly equal-sided to sort of pointing northwest. Right over here, up near the top, they start to point east. Okay? And so what's happening is one of the variables is growing while the others shrink as you move from left to right. Okay? And you know, here's the thing, right? So I'm looking at this and I'm thinking, okay, how do I describe this plot in words to you guys? You're all looking at it, right? How do I describe this plot in words to you? And it's kind of hard. And it's kind of hard for a couple of reasons. One reason is that the part of my brain that interprets pictures is not the same as the part of my brain that forms words to describe things. So it's actually hard work to think about how the pattern evolves as you move across the picture. So I can look at it and I can see how that pattern evolves, but verbalising it actually causes me cognitive load, right? And that's an interesting feature because describing something and looking at something are actually quite different. And what's even harder is to try and understand what does the five-dimensional relationship look like. So this is an interesting graph because I've actually not lost any information here. This graphic summarises all 5 dimensions of my data, so all the information's in there, but unfortunately my brain is too small to understand what it's telling me. That's sad in one way, right? And, you know, I mean, I don't know, I'm probably a pretty smart guy, and I'm guessing you guys are all smart too, right? Because you don't land in a third-year class unless you're smart. But I'm guessing most of you would have the same struggle that I'm having in terms of seeing the big picture here. Does anyone sort of feel like understand this relationship completely by looking at that plot? Lots of people going this, the universal symbol for no, right? And so herein lies the challenge, right? I can, by doing a graph like this, do the ultimate in dimension reduction. I've got 5-dimensional data. I can produce a 2-dimensional analogue in which all the information is preserved. Okay? There is no information loss here, but in some ways that's not very satisfying because even though I've lost no information, none of you can actually see what's going on. Okay? And so I think in general you have to be quite modest in your attempts to reduce dimension. Okay? So I probably, you know, if you were saying to me, what's the best way to display this data, I probably wouldn't produce this and say, voila, here is the answer. Because your capacity to understand what it's telling you is probably not very high, irrespective of how smart you are. I should probably do something a little bit less ambitious. So instead of doing that one, I might say, okay, fine, I'm not going to try to summarise all 5 dimensions in the 2D plot. I'm going to go for 4 dimensions instead. So basically amp down what I'm trying to do. So this time I'm going, okay, heat evolves on the y-axis, CA3A is on the x-axis, and I'm only going to encode 2 of the other variables, CA3S and CAAF. That should be an A, not a 2. And I get a picture that's a little bit easier to see what's going on because you don't have to keep 3 things in mind, you only have to keep 2 things in mind as you look at the symbols. Still a bit challenging, but not too bad. What you'll notice, it's actually pretty clear. Lower left-hand corner of the plot, all the rectangles are standing up nice and tall and they're skinny. And then when you move to the top right corner of the plot, they're all squatting down and they're short and fat. And that happens pretty much continuously as you move across the curve, right? So tall and thin, short and squat, and you can sort of see that evolve as you move across the curve. And that's a pretty good picture for this data. That's a pretty good picture for this data because you're capturing 4 dimensions in 2 dimensions and the message is not that hard to get. I think the stars make it a little bit harder. So I think this is a good representation for this particular data. Okay. Now, just thinking forward a little bit because you guys are probably going to start looking at the project stuff. If you are going to look at the project data involving the insurance, symbol plots are likely to be very useful because in that insurance data, you're going to be trying to relate a response to multiple covariates. So being able to visualise what happens to that response as those covariates change is going to be part of the challenge. And one of the central messages of today is don't just rush into fitting models because you get coefficients that might not make a whole lot of sense if you actually think about them. So start by trying to do symbol plots to see where you go, okay? Just very quickly, we're almost out of time. You can just encode one variable by using squares, but remember what I said yesterday. Squares are based on only one number, the side length, and they grow faster than they should. So when a number doubles, the size of the square should double. What's happening instead is the size of the square quadruples because 2 squared is 4, right? and that's a problem. So those squares that are up the top look way bigger than these squares down here, and it's not an accurate rendering of what's going on with the data. These numbers aren't doubling or tripling, they're actually going up much slower. Okay, so be careful using squares and using circles for that reason. Very quickly, not much really to say here except the syntax is pretty simple. When you use symbol plots, the basic command is symbols.